Hello everyone, and welcome to today's lecture video, which is on the Euler MacLaurin summation formula. This is going to be a basic introduction to this formula, meaning I'm not going to discuss the error term in the formula, and we're going to derive it in much the same way that Euler derived it himself back in the 1700s. And even without deriving the formula in its final form, which includes an error term, it's still an incredibly powerful and useful formula, as I hope you'll all see today. So in today's video, we're going to do a few things. First, we're going to actually derive the Euler MacLaurin summation formula without the error term. And then once we have this formula, we're going to show how to apply it in a couple interesting cases. We're going to look at how it can be used to derive Faulhaber's formula in the case of taking sums of x to the fourth, where x is an integer, so 1 to the fourth plus 2 to the fourth plus 3 to the fourth, etc. And we'll also show how Euler used it in his solution to the famous Basel problem, which is the problem of computing the sums of the reciprocals of squares, so 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. Very important problem in the history of mathematics, as we'll see. So while those particular uses of the formula are very interesting and fruitful, I want to speak more generally about the motivation behind deriving the Euler MacLaurin summation formula. And it comes from this issue. Integrating a function is often conceptualized as a continuous summation of the values of the function. So I'm going to draw our coordinate axes, x and y here, and we can just draw some function, some general function there. Okay. So that'll be our function y equals f of x. And then if we want to find the definite integral for the function y equals f of x from some value, say 1 to n, what we do is we take the limit of summing up these little rectangles that are bounded between the x-axis and the function y equals f of x. So each of these rectangles here will have a height of f of x. And the idea behind the Riemann integral is that as we sum up more and more of these rectangles, so the rectangle's base becomes narrower and narrower and narrower, and we're summing up more and more of them in this interval between 1 and n, that approximation for the area under the curve gets better and better and better. So here I've drawn f of x, which I've indexed by k, so that's f of x sub k, and the width of that tiny rectangle would be delta x. So each of these rectangles has a height f of x sub k at each of the x sub k where we're basing the rectangle, and they're all being multiplied by delta x. And so then if I take the limit as delta x goes to 0, as these rectangles again become narrower and narrower, and we're summing up more and more of them, that sum will equal the value of the definite integral from 1 to n of f of x dx. So the Riemann integral implies that we can get an approximation for the value of the integral by just discretely summing f of x wherever x is an integer. So for example here I'll draw rectangles with width 1 and height f of x, so the area of each individual rectangle is just f of x at whatever value x happens to be. And so the sum of the areas of all these rectangles will just be f of 1 plus f of 2 plus f of 3 dot 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 all the way up to f of n minus 1 plus f of n. I'm assuming here that n is an integer, of course. Again, this area, summing up the areas of all the rectangles, will just equal the sum from k equals 1 to n of f of k, where k equals 1, 2, 3, 4, all the way up to n. And we know that the sum of the areas of all these rectangles will be an approximation of the value of the integral from 1 to n of f of x dx. And so a natural question emerges, and that question is this: is there some kind of formula connecting the discrete summation of the values of f of x, the values of f of x at x equals 1, x equals 2, x equals 3, and so on up to n, and the integral, the continuous summation of the values of f of x from 1 to n? And the answer is actually yes, amazingly. And that is the Euler MacLaurin summation formula. It's a formula that connects the discrete summation of a function to its integral, to its continuous summation. So here's Leonhard Euler's, and I suppose also Colin Maclaurin's, brilliant idea, and that's to consider some unspecified function, which we'll call f of x, and I'll just draw what that function could look like. So I'll lay down some axes here, and this is our function y equals f of x. And we want to take the sum of all the values of f of x from x equals 1 all the way up to x, and I'm assuming here that x itself is an integer. So I've written on the x-axis 1, 2, 3, dot, 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 up to x minus 1 and then x. And so this first value on the y-axis is f of 1, and the next value I'm writing here is f of 2. And these rectangles, each of them has a width of 1, and the height of each rectangle equals f of x at whatever value x happens to take. So I'll just fill out the rest of these rectangles here. And then if we were to total up the sum of all the areas of these rectangles, that would be the sum that we're looking for. It would equal f of 1 plus f of 2 plus f of 3, dot, 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 all the way up to f of x minus 1 plus f of x. And now when we consider this sum, which is related to f of x, the sum of the values of f of x at x equals 1, x equals 2, x equals 3, and so on up until x, we might realize that that sum is itself a function of x. In much the same way as the definite integral, which represents the area under the curve, is a function of x. It's actually an antiderivative of f of x. This sum function depends on our choice of x. And we can write it as s of x equals f of 1 plus f of 2 plus dot, 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 all the way up to plus f of x minus 1 plus f of x. So here's the great insight. Because the function s of x, representing the sum of f of x at x equals 1 and x equals 2 and x equals 3 all the way up to x, because s of x is itself a function of x, s of x can be represented as a Taylor series centered at x. So let's see what form that Taylor series representation for s of x would take. Now, you may be used to seeing x as the variable for a Taylor series, and then when we want to center the Taylor series at some point, we usually label that point C. I'm going to write it a little differently here. I'm going to make my variable t because we're centering the Taylor series at the point x. So with that change in mind, we'll write s of t, t is our variable, not x, s of t equals s of x plus s prime of x times t minus x to the first power all over 1 factorial plus s double prime of x times t minus x squared all over 2 factorial plus s triple prime of x times the variable t minus x cubed all over 3 factorial plus the fourth derivative of s evaluated at x times t minus x to the fourth all over 4 factorial plus the fifth derivative of s evaluated at x times our variable t minus x, quantity to the fifth, all over 5 factorial plus dot, 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 and so on. That's our pattern. That's the general form of a Taylor series. Here I've made my variable t, and I've centered the Taylor series at the value x. But now we're going to do something very clever. We're going to let t equal the value x minus 1. When we do that, when we let our variable t equal the value x minus 1, then the expression t minus x, that would equal x minus 1 minus x. The x's cancel, and that just equals negative 1. So in this Taylor series that I've written, I will replace t with x minus 1, so I'll have s of x minus 1 equals s of x, no change there, plus s prime of x times negative 1 to the first, all over 1 factorial, plus s double prime of x times negative 1 squared, all over 2 factorial, plus s triple prime of x times negative 1 cubed, all over 3 factorial, and so on. And now I can simplify further because negative 1 to an even power just equals positive 1, and negative 1 to an odd power just equals negative 1. So I can rewrite this formula as s of x minus 1 equals s of x minus s prime of x over 1 factorial plus s double prime of x over 2 factorial minus s triple prime of x over 3 factorial plus the fourth derivative of s evaluated at x over 4 factorial, and so on. Now, so far in our manipulation of this Taylor series, we have not made any explicit reference to what kind of function s of x is. But we know by definition that s of x is the sum of the values of f of x. Therefore, we can write s of x minus 1 equals s of x minus f of x. Now, let's think about why that would be. S of x would equal the area of all of these rectangles that I'm outlining in yellow here. The values of f of x from x equals 1 all the way up to x. That would be s of x, the sum of all of those values. S of x minus 1 would exclude that final rectangle whose value equals f of x. So s of x minus 1 would be represented by the area that I'm going to outline now in red. It would equal the value of s of x minus that final contribution from the rectangle whose area equals f of x. So we have s of x minus 1 equals s of x minus f of x, and I'm going to plug that into our Taylor series up here. For s of x minus 1, I have written s of x minus f of x, but if you look at this equation now, the s of x on the left hand and the s of x on the right hand cancel. So I'm left with negative f of x equals this Taylor series. So then when we multiply both sides of this equation by -1, that flips the signs, and we're left with f of x equals s prime of x over 1 factorial minus s double prime of x over 2 factorial plus s triple prime of x over 3 factorial, and so on. Well, that equation is so important that I've put a box around it and put it at the top of the screen. And now our goal for the rest of this video is going to be to invert this equation. In other words, we're going to try to find a way to shift things around so that we have s of x on one side of the equation and only terms involving f of x on the other side of the equation. We'll be finding s of x purely in terms of f of x and its derivatives. Well, how might we go about doing that? Well, to do this, we should start by noticing what happens if we differentiate this expression. If we differentiate f of x with respect to x, we get f prime of x equals s double prime of x all over 1 factorial minus s triple prime of x all over 2 factorial. Right, the factorials are just constants, so they're not affected by this differentiation, so plus s4 of x, or the fourth derivative of s with respect to x, evaluated at x, over 3 factorial. I'll just say minus s5 of x, and hope you understand what I mean by that. I mean the fifth derivative, all over 4 factorial, plus s6 of x, all over 5 factorial, and so on. And now we just have to do some fairly straightforward algebra, because when we compare these two equations, we might notice that we can cancel the s double prime term if we simply multiply the second equation, the f prime of x equation, by 1/2, and then add the top and bottom equations together. So I'm going to do that now. I'm going to multiply both sides of the bottom equation by 1/2, and then I'm going to add the top and bottom equations together. So adding the terms on the left-hand side together, we get f of x plus 1/2 times f prime of x equals, now we'll add the right-sided terms together, s prime of x over 1 factorial. And then we'll see that the s double prime terms cancel. The minus s double prime of x over 2 factorial gets completely canceled out in the top equation by the plus s double prime of x over 2 times 1 factorial, which also just equals 2 factorial. So those two terms cancel. And then we're left with plus s triple prime of x over 3 factorial minus s triple prime of x over 2 times 2 factorial. I'll close parenthesis on that. And then we get our s4 terms, so minus s4 of x, that's the fourth derivative of s, of x, over 4 factorial plus s4 of x over 2 times 3 factorial plus S5 of x over 5 factorial minus S5 of x over 2 times 4 factorial. I'll put a parenthesis around that. Then our next set of terms would be minus S6 of x over 6 factorial plus S6 of x over 2 times 5 factorial, and so on. Right, the series on the right-hand side of the equation is infinite. So we've gotten rid of the s double prime term on the right-hand side, and I've written our new equation on top here, and I've written our original formula for f of x below that. And now we want to repeat that process to get rid of the s triple prime terms. So to do that, I'm going to find the second derivative of f of x. So once again, we start with f prime of x, that equals s double prime of x over 1 factorial minus s triple prime of x over 2 factorial plus s quadruple prime of x over 3 factorial minus s5 of x over 4 factorial plus s6 of x over 5 factorial. And now we just differentiate this again, minus dot dot dot, of course. So we have f double prime of x would equal s triple prime of x over 1 factorial minus s quadruple prime of x over 2 factorial plus s5 of x over 3 factorial minus s6 of x over 4 factorial plus s7 of x over 5 factorial minus dot dot dot. Okay, I've moved that equation up, and now we want to cancel the s triple prime of x terms from both of these equations. So looking at the top equation here, where I have s triple prime of x over 3 factorial minus s triple prime of x over 2 times 2 factorial, we need a common denominator there. So s triple prime of x over 3 factorial minus s triple prime of x over 2 times 2 factorial, that would equal s triple prime of x over 6, right? 3 factorial is just 3 times 2 times 1, which equals 6. And then 2 factorial times 2, that just equals 2 times 2 times 1. So that would be s triple prime of x over 4. So the common denominator here is 12. So I have 2 times s triple prime of x over 12 minus 3 times s triple prime of x over 12. And so we find that this quantity is equal to negative s triple prime of x over 12. So let me rewrite that there. So this is now in the top equation s prime of x plus negative s triple prime of x over 12 plus all the other terms. So to cancel out that term, that negative s triple prime of x over 12, we should multiply the bottom equation by 1/12, and then sum the two equations together, like we did before. So I'm going to do that here. I'm going to multiply the bottom equation on both sides by 1 over 12. That 1 over 12, of course, distributes to all those terms on the right-hand side. Then we're going to sum the equations together. And when we do that, summing the left-hand terms first, we get f of x plus 1/2 times f prime of x plus 1/12, 1 over 12, times f double prime of x equals, and now here are the right-hand terms, that s prime of x again goes untouched. And then we cancel the s triple prime of x terms. And then we have minus s quadruple prime of x over 4 factorial plus s quadruple prime of x over 2 times 3 factorial minus s quadruple prime of x, this is coming from the bottom equation, over 12 times 2 factorial. And then the s5 terms, we have plus s5 of x over 5 factorial minus s5 of x over 2 times 4 factorial. Okay, plus s5 of x over 12 times 3 factorial. And I can put a parenthesis around those terms. Minus s6 of x over 6 factorial plus s6 of x over 2 times 5 factorial minus s6 of x over 12 times 4 factorial plus dot dot dot. Now, if we look closely at this equation, we'll realize that we actually accomplished more than we set out to do by multiplying the equation for f double prime of x by 1 over 12 and adding that to our previous equation. Because if we look at the s4 terms, the fourth derivative of s, we'll see that negative s4 of x over 4 factorial plus s4 of x over 2 times 3 factorial minus s4 of x over 12 times 2 factorial, we'll see that these s4 terms actually cancel each other out. So negative s4 of x over 4 factorial is just 4 times 3 times 2 times 1, which is 24, plus s4 of x over 2 times 3 factorial, that's 2 times 3 times 2 times 1, which equals 12, minus s4 of x over 12 times 2 factorial, so that also equals 24. Our common denominator here is 24, so we have s4 of x, I'll just pull that out, and then in parentheses I'll have minus 1 over 24 plus 2 over 24 minus 1 over 24. That equals 0. So a nice thing happened for us here. We didn't have to do anything to cancel the s4 terms. They were canceled out in that previous step where we multiplied f double prime of x by 1 over 12. Since I didn't have to multiply f triple prime of x by anything and add it to that equation, on the left-hand side I'm just going to write plus 0 times f triple prime of x. That's a void entry, but it helps us keep track of all of the derivatives of f of x in this equation. But moving forward, to cancel the s5 of x terms, we need to look at f quadruple prime of x. So I have here f of x, we've seen that before, and now f quadruple prime of x will just differentiate f of x 4 times. So this will give us that f quadruple prime of x equals s5 of x over 1 factorial minus s6 of x over 2 factorial plus s7 of x over 3 factorial minus s8 of x over 4 factorial plus dot dot dot. Now we've seen this procedure twice already. We should know what to do. Looking at the top equation, we want to simplify the s5 of x terms before we figure out how to cancel them. So we have s5 of x over 5 factorial minus s5 of x over 2 times 4 factorial plus s5 of x over 12 times 3 factorial. So now I'll just factor out that s5 of x term. So the sum of these three terms together will equal s5 of x times, open parenthesis, 1 over 5 factorial. 5 factorial is 120, minus 1 over 2 times 4 factorial, so that's 1 over 48, plus 1 over 12 times 3 factorial, that's 1 over 72. The common denominator here is 720, so this will equal S5 of x times, open parenthesis, 6 over 720 minus 15 over 720 plus 10 over 720, which equals S5 of x times 1 over 720. So we can simplify that S5 term in the top equation. That's just going to equal plus S5 of x over 720. And then to cancel that S5 of x term, we need to multiply the bottom equation by negative 1 over 720, and then add the two equations together. Let's do that. I'm going to multiply f4 of x by negative 1 over 720, and I'm going to multiply all the terms on the right by negative 1 over 720. So I'm distributing that there. And then we're going to add the equations together. And when we do that, the left-hand terms, we've got f of x plus 1/2 times f prime of x plus 1/12, 1 over 12, times f double prime of x plus 0 times f triple prime of x. And then, here we go, minus 1 over 720 times f quadruple prime of x. Those are the left-hand terms, and now the right-sided terms, those will equal s prime of x, that continues to remain untouched, and then the s5 terms cancel out, so then we have minus s6 of x over 6 factorial plus s6 of x over 2 times 5 factorial minus s6 of x over 12 times 4 factorial. Now when we look at the S6 term in the second equation that we're adding, when we sum these equations together, we have minus S6 of x over 2 factorial, but we're multiplying that by negative 1 over 720, so the minus signs cancel and we get plus S6 of x over 720 times 2 factorial. So let me just add that term to our resultant equation when we sum these two equations up top together. So that's plus S6 of x over 720 times 2 factorial plus dot dot dot. So let me move that resultant equation to the top of the screen here. And now it turns out that the S6 terms cancel each other out. So let's see how that works. So it turns out we have the following, looking at these S6 terms. We have negative S6 of x over 6 factorial plus S6 of x over 2 times 5 factorial minus S6 of x over 12 times 4 factorial. And now just to continue the pattern here, I'll have plus 0 times S6 of x over 3 factorial. Obviously, we don't have a 0 up there, but I can include it as a void entry. Minus S6 of x over 720 times 2 factorial. So that'll equal S6 of x, factoring that out, times negative 1 over 720 plus 1 over 240 minus 1 over 288 plus 0 plus 1 over 1,440. So it turns out that 1,440 is the common denominator here. So this will equal S6 of x times, open parenthesis, negative 2 over 1,440 plus 6 over 1,440 minus 5 over 1,440 plus 1 over 1,440, and that equals S6 of x times 0. So those S6 terms cancel out, and I'm left with the above expression equaling S prime of x plus S7 of x times some terms that we didn't calculate, plus all the other terms in S8 of x and S9 of x, and so on. Well, space has not permitted me to show what would happen with the S7 of x terms, but I hope that you can go back and see the pattern and take it from me that if we had carried out our mathematical operations further, we would have had the following for the S7 of x terms. The equation above equaling S prime of x plus S7 of x times, open parenthesis, 1 over 7 factorial minus 1 over 2 times 6 factorial plus 1 over 12 times 5 factorial minus 0 times 1 over 4 factorial plus 1 over negative 720 times 3 factorial minus 0 times 1 over 2 factorial, close parenthesis, and then minus dot 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 for the S8, S9, and so on terms in the equation. So then when we unpack this, this will equal S prime of x plus S7 of x times, open parenthesis, 1 over 5,040 minus 1 over 1,440 plus 1 over 1,440 minus 1 over 4,320, close parenthesis, minus dot dot dot. Now we see that the 1 over 1,440 terms within the parenthesis cancels, so we are left with this equaling S prime of x plus S7 of x times, open parenthesis, now finding a common denominator, 6 over 30,240 minus 7 over 30,240, close parenthesis, minus dot 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 again. Well, 6 over 30,240 minus 7 over 30,240 is negative 1 over 30,240, so I'll just move that term up here. So we have that the expression above equals S prime of x minus 1 over 30,240 times S7 of x minus S8 of x times some coefficients that we would need to determine, plus S9 of x times some more coefficients, and so on. And now we want to cancel the S7 term. So to do that, we need to find the sixth derivative of f of x. So f6 of x, and that would equal S7 of x over 1 factorial minus S8 of x over 2 factorial plus S9 of x over 3 factorial minus dot dot dot. So hopefully by now we know the drill. We multiply both sides of this equation for f6 of x by 1 over 30,240. So I'm going to distribute that on the right-hand side of this equation. And then to cancel the S7 of x terms, we add these two equations together. And when we do that, we get f of x plus 1/2 times f prime of x plus 1/12 times f double prime of x plus 0 times f triple prime of x minus 1 over 720 times f4 of x plus 0 times f5 of x. And now I'm going to add that term on the left in the second equation, plus 1 over 30,240 times f6 of x. This whole thing will equal S prime of x, and then the S7 of x terms cancel, so the next term would be minus S8 of x times some factors that we would need to calculate, plus S9 of x times some more factors that we would need to calculate, and so on. Well, as you can see, calculating this formula by hand takes a good bit of work. At this point, though, we may want to take a step back from what we're doing and ask ourselves, what is the general pattern here? And more specifically, how are we determining the coefficients for f of x and all its higher order derivatives on the left-hand side of the equation? So let's consider these coefficients for f of x and its derivatives and what we've been doing so far. To summarize our work, I'll make a table here, and in the left column I'll have fn of x, the nth derivative of f of x. And in the right column, I'll have the coefficient that multiplies fn of x, so I'll call that coefficient c of n. So if I start with the 0th derivative of f, that's in other words just f of x, that's being multiplied by 1 there in the equation, so c of 0 would just equal 1. For f prime of x, our coefficient is 1/2. And you may recall that we found that coefficient in our efforts to cancel out the term s double prime of x over 2 factorial from the Taylor series for f of x. Next, for f double prime of x, our coefficient is 1/12, And we got that by canceling out the term s triple prime of x times 1 over 3 factorial minus 1 over 2 times 2 factorial. And then for the term after that, the coefficient of f triple prime of x was just 0. And you may recall that we found that because the terms multiplying s4 of x, namely negative 1 over 4 factorial plus 1 over 2 times 3 factorial minus 1 over 12 times 2 factorial, that those terms cancel out, that equals 0. So I've extended the table up a little bit here, and now we want to look at the coefficient of f4 of x. Well, we found that that would be negative 1 over 720, and we got that in our efforts to cancel out the term s5 of x times 1 over 5 factorial minus 1 over 2 times 4 factorial plus 1 over 12 times 3 factorial minus 0 times 1 over 2 factorial. And then for our coefficient of the f5 of x term, we found again that that equals 0. And the reason for that is that the factors multiplying s6 of x, namely negative 1 over 6 factorial plus 1 over 2 times 5 factorial minus 1 over 12 times 4 factorial plus 0 times 1 over 3 factorial minus 1 over negative 720 times 2 factorial, close parenthesis, that those terms cancel each other out and equal 0. And then the last coefficient we calculated, the f6 of x coefficient, we found that equals 1 over 30,240, and we got that by canceling out s7 of x times 1 over 7 factorial minus 1 over 2 times 6 factorial plus 1 over 12 times 5 factorial minus 0 times 1 over 4 factorial plus 1 over negative 720 times 3 factorial plus 0 times 1 over 2 factorial. Close parenthesis. Well, you can see that all of those coefficients in green that I've included in the parentheses are actually the c sub n, so I can just make them all the same color, so I've made them all blue here. And what this table reveals is that there's actually a recursive pattern for calculating the c sub n. Since 1 equals c sub 0, we then find that c sub 1 equals 1/2, which is negative c sub 0 times negative 1 over 2 factorial. Going down one line, c sub 2 equals 1/12, which is negative, open parenthesis, c sub 0 times 1 over 3 factorial, minus c sub 1 times 1 over 2 factorial. So I hope that the pattern is clear here, and we can also see that it's recursive. Each new c sub n that we derive depends on what we derived in the line above it. And remember, we're deriving these c sub n terms in order to cancel the higher order derivatives of s of x on the right-hand side of the equation. Now, if we were somehow able to infinitely continue this process of deriving the c sub n and canceling all the s sub n of x terms on the right-hand side of the equation, obviously that's impossible, but imagine that we could do that we could cancel all of them. Then we would get the equation f of x plus 1/2 times f prime of x plus 1 over 12 times f double prime of x plus 0 times f triple prime of x minus 1 over 720 times f quadruple prime of x plus 0 times f5 of x plus 1 over 30,240 times f6 of x. And now we didn't calculate the next coefficient, but it actually turns out to be 0. So plus 0 times f7 of x. And we didn't do the next term either, but Euler did. And it turns out to be minus 1 over 1,209,000 600 times f8 of x plus all the other terms we would have on the left-hand side, and that would all equal s prime of x. That's the only term on the right-hand side that survives cancellation in all of these steps. And then without changing the content of this formula, we might realize that we can clean it up a little bit by making the signs alternate. Then we would have f of x minus negative 1/2 times f prime of x plus 1/12 times f double prime of x minus 0 times f triple prime of x plus negative 1 over 720 times f4 of x, and so on. We'll see in a moment that that isn't only an aesthetic choice. The formula makes more sense when the signs alternate. We might see another pattern here, which is that each of the c sub n is divisible, actually, by n factorial. So I can factor out a factorial from each of these terms. So to begin with, for my coefficient multiplying f0 of x, or f of x, I have 1 over 0 factorial times 1 times f of x. Then, for the next term, I can just divide out 1 factorial, so minus 1 over 1 factorial times negative 1/2 times f prime of x, plus, so for 1/12 I can divide out 2 factorial, and it will become 1 over 2 factorial times 1/6 times f double prime of x. And then my next term, 0, is divisible by anything, so I can divide out 1 over 3 factorial. So this will be minus 1 over 3 factorial times 0 times f triple prime of x. And then my next term after that is plus negative 1 over 720. Well, that's divisible by 4 factorial, so I can rewrite it as plus 1 over 4 factorial times negative 1 over 30 times f4 of x. And then I have minus, again 0 is divisible by anything, so minus 1 over 5 factorial will work, times 0 times f5 of x. My next term is plus 1 over 30,240. Well, that's divisible by 6 factorial, so I can rewrite it as plus 1 over 6 factorial times 1 over 42. The term after that again is 0, so I can divide it by 7 factorial without changing the content of this equation. So this will be minus 1 over 7 factorial times 0 times f7 of x. And then my term after that, negative 1 over 1,209,600, that's divisible by 8 factorial. So I can rewrite that as plus 1 over 8 factorial times negative 1 over 30 times f8 of x minus, well, you might guess that the next term is going to be 0 times f9 of x, but the point is that this will continue infinitely. And then on the right-hand side of the equation, all I'll have is this equaling s prime of x. And this factoring out each of those factorials in each term was actually a very consequential step, because Euler realized that once you do this, the numbers that you have that I've written in green, the coefficients there in green, are actually the numbers in a sequence that's very important in mathematics. The sequence of numbers is called the Bernoulli numbers because they were discovered by Jacob Bernoulli. They appear in many different contexts in mathematics, and we see them here. And now we're ready to take the final step in deriving the Euler MacLaurin summation formula and solve for s of x in terms of f of x and its derivatives of all orders by integrating both sides of this equation. So when we do that, when we integrate the left-hand side of the equation and the right-hand side of the equation, we have this integral on the left-hand side of that entire sum equals the integral of s prime of x dx. And then when we apply the integral on the left-hand side, that first term becomes the integral of f of x dx. The next term becomes minus 1 over 1 factorial times negative 1/2 times f of x instead of f prime of x. The next term then becomes 1 over 2 factorial times 1/6 times f prime of x instead of f double prime of x, and so on. Each of these higher order derivatives of f of x gets antidifferentiated one time. And then on the right-hand side of the equation, the integral of s prime of x dx is just s of x. So here we have our final form of our summation formula derived independently by both Leonhard Euler and Colin Maclaurin. This amazing formula allows us to calculate the sum of the values of f of x on the integers all the way from 1 to x if x is itself an integer, purely in terms of f of x, its integral, and its derivatives of all orders. Now there's only one caveat here, which is that the left-hand side of this equation is an infinite sum. Now, in the real world, we would never be able to calculate an infinite sum. We would truncate it somewhere, and then we would want to have some kind of remainder term that bounds the error. Well, Euler and Maclaurin never gave us that. That was discovered later by Poisson, and I'll make that the subject of a later video. But you'll see that in many cases, the Euler MacLaurin summation formula, as Euler and Maclaurin derived it, is still extremely powerful and extremely useful. But before we get into some of the applications of the Euler MacLaurin summation formula, I just want to take a step back and address the issue of what are these Bernoulli numbers that show up in the formula? Well, there's no explicit formula for them. But there are numerous recursive formulae for the Bernoulli numbers. And one of the formulas that occurs very commonly in the literature is this one. It says that the nth Bernoulli number, b sub n, in the sequence of Bernoulli numbers equals the negative of the sum indexed from k equals 0 to n minus 1 of n choose k, that's the binomial coefficient n choose k, times b sub k, the kth Bernoulli number, over n plus 1 minus k. Now that might look like something out of left field, but this definition actually emerges naturally from the way that we constructed the c sub n in our development of the Euler MacLaurin summation formula. So to see how this works, let's take a concrete example. Let's let n equal 6. We found c sub 6 in the Euler MacLaurin summation formula equals 1 over 30,240. And we derived it from that line in our table of the c sub n that I've copied and pasted here. So we saw that in general, c sub n equals 1 over n factorial times b sub n. So for the case of n equals 6, we would write 1 over 6 factorial times b sub 6 equals this expression that we use to calculate c sub 6. In fact, I can rewrite all the c sub n in this formula in terms of the related Bernoulli numbers. So c sub 0 becomes b sub 0 over 0 factorial, c sub 1 becomes b sub 1 over 1 factorial, and so on. And now we're already pretty close to deriving our recursion relation for the nth Bernoulli number. We'll multiply both sides of this equation, in this instance by 6 factorial. So when I do that, I have 6 factorial over 6 factorial on the left-hand side. Those cancel. On the right-hand side, I'm distributing the 6 factorial to all of those terms. And then the next thing I'll do is factor out the leading term from each of the purple factorials that I've written. All the factorials I've put in the denominator that I've written in purple. So then I'll have b sub 6 equals negative, open parenthesis, b sub 0 over 7. That's the leading term that I factored out from 7 factorial, times 0 factorial times now 6 factorial, plus b sub 1 over 6, that's the leading term I factored out there, times 6 factorial over 1 factorial times 5 factorial, plus b sub 2 over 5 times 6 factorial over 2 factorial times 4 factorial, plus b sub 3 over 4 times 6 factorial over 3 factorial times 3 factorial, plus b sub 4 over 3 times 6 factorial over 4 factorial times 2 factorial, plus b sub 5 over 2 times 6 factorial over 5 factorial times 1 factorial. Close parenthesis. Now, why did we rearrange the terms in that way? Well, when we do this, we see that the terms that I have in orange here are the binomial coefficients of 6 choose n. Recall that the general definition for the binomial coefficient n choose k is n choose k equals n factorial over, open parenthesis, n minus k, close parenthesis, factorial, times k factorial in the denominator. So I'm going to rewrite these orange terms as 6 choose 0, and the next one will be 6 choose 1, and then so on, 6 choose 2, 6 choose 3, 6 choose 4, and 6 choose 5. Therefore, we can write b sub 6 in a more concise way as the negative of the sum indexed from k equals 0 to 5 of b sub k over 6 plus 1 minus k times 6 choose k. And in general, we can write that b sub n equals the negative of the sum indexed from k equals 0 to n minus 1 of b sub k over n plus 1 minus k times the binomial coefficient n choose k. So let me put a box around this because it's an important recursive definition for the Bernoulli numbers. And as you can see, again, it emerges naturally from our process of determining coefficients in the Euler MacLaurin summation formula. So for reference, I'll just list the first 10 Bernoulli numbers. I believe Euler calculated the first 20 or so by hand, which is quite a feat. But at any rate, we have b sub 0 equals 1, b sub 1 equals negative 1/2, b sub 2 equals 1/6, b sub 3 equals 0, b sub 4 equals negative 1 over 30, b sub 5 again equals 0, b sub 6 equals 1 over 42, b sub 7 equals 0, b sub 8 again equals negative 1 over 30, b sub 9 equals 0, and b sub 10 equals 5 over 66. This is the first Bernoulli number which has a number other than 1 in the numerator. And it turns out that actually most Bernoulli numbers are not of the form 1 over something. And just upon visual inspection of this list of the first 10 Bernoulli numbers, we might notice a few patterns right away. For example, that all the Bernoulli numbers are rational numbers, that all of the odd index Bernoulli numbers greater than b sub 1 are 0, that the non-zero Bernoulli numbers alternate signs. There are a number of patterns that can be proven, but that would take us too far afield from the main topic of this video. Instead, what I would like to do is illustrate a couple very cool applications of the Euler MacLaurin summation formula. But before I do that, let's just recap what we've accomplished so far. Well, following Euler, we derived a summation formula for a given function f of x that gives us our sum function s of x, which equals f of 1 plus f of 2 plus f of 3 plus ... all the way up to plus f of x. And this formula gives us s of x purely in terms of f of x, its integral, and its derivatives of all orders. Furthermore, we found that the Euler MacLaurin summation formula is intimately related to the sequence of numbers known as the Bernoulli numbers. Namely, the Euler MacLaurin summation formula says that s of x equals the integral of f of x dx minus 1 over 1 factorial times negative 1/2, that's b sub 1, times f of x, plus 1 over 2 factorial times 1/6, that's b sub 2, times f prime of x, minus 1 over 3 factorial times 0, that's b sub 3, times f double prime of x, plus 1 over 4 factorial times negative 1 over 30, that's b sub 4, times f triple prime of x, and so on. Well, we've done a lot of work to derive this formula, and it's time to test it out. And the first example that I want to give you to show how the Euler MacLaurin summation formula works is to apply it to the question of sums of powers. So we want to find 1 to the 4th plus 2 to the 4th plus 3 to the 4th power plus some succession of integers raised to the 4th power plus ultimately some integer x to the 4th, which will be of our choosing. So let's do that. So we'll let f of x equal x to the 4th. And we're going to plug that in for f of x into the Euler MacLaurin summation formula. Now I want to stress that formulas for the sums of powers have been discovered years prior to Euler and Maclaurin discovering their much more general summation formula. These sums were compiled and published by a mathematician named Faulhaber, and it was actually Bernoulli who then took them and wrote them in the following form. So take, for example, the sum of 4th powers. If we want the sum indexed from k equals 1 to n of k to the 4th, Bernoulli realized that the most efficient and uniform way to write that was as 1 over 5 times open parenthesis n to the 5th plus 5 over 2 times n to the 4th plus 10 over 6 times n cubed plus 0 times n squared minus 5 over 30 times n, close parenthesis. And if you scrutinize that for a moment, you might see that the Bernoulli numbers are actually hiding in that formula. Bernoulli himself noticed that, and that's why those numbers are named after him. But what Jacob Bernoulli published was merely an empirical observation on the first several power sum formulae. It was a brilliant observation, but it didn't have a theoretical foundation. We now have a general formula for the summation of functions with a theoretical basis in calculus, and a very general formula, and we'll see that Faulhaber's formula for summing the 4th power of integers comes right out of the Euler MacLaurin summation formula. So let's see it in action. This is the Euler MacLaurin summation formula in the blue box up there, and I'm going to let f of x equal x to the 4th. So when I do that, when I plug in x to the 4th for f of x, the integral of x to the 4th dx, and then I'll plug in x to the 4th in the next term, and then I'll take the derivative to find 4x cubed instead of f prime of x. The second derivative would be 12 times x squared. The third derivative will be 24 times x to the 1st. The fourth derivative will just be 24 times x to the 0. And then the fifth derivative, sixth derivative, seventh derivative, all subsequent derivatives just equal 0. And all of the odd Bernoulli numbers greater than b sub 1 are 0, so those terms also cancel. And so in the end, I'm left with s of x equaling this left-hand sum, which is actually finite. Now what about that term in the equation, integral of x to the 4th dx? That's an indefinite integral. It equals x to the 5th over 5 plus c, where c is some constant to be determined. So we need to figure out what this constant c must equal. To find c, we can set x equal to 1. Then we have s of 1 would just be the sum from k equals 1 to 1 of k to the 4th, which equals 1 to the 4th, which equals 1. So my integral of x to the 4th dx, that equals x to the 5 over 5 plus c. And now to determine c, I'm going to plug in 1 for x. Now we already saw that s of 1 equals 1. Subbing in 1 for x, 1 to the 5th over 5 plus c minus 1 over 1 factorial times negative 1/2 times 1 to the 4th plus 1 over 2 factorial times 1/6 times 4 times 1 to the 3rd plus 1 over 4 factorial times negative 1 over 30 times 24 times 1 to the 1st power equals 1. Now when we work this out numerically, we get 1/5 plus c plus 1/2 plus, well, 1 over 2 factorial times 1/6 times 4. The 2's there cancel. So this becomes plus 2 over 6, or plus 1/3. And then the 1 over 4 factorial cancels out the 24 there. So that last term equals minus 1 over 30. And this whole thing equals 1. So finding a common denominator here, I have 6 over 30 plus c plus 15 over 30 plus 10 over 30 minus 1 over 30. So I have c plus 30 over 30 equals 1. So c plus 1 equals 1. C equals 0. So then for that first term in the summation in the box, the integral, the indefinite integral of x to the 4th dx equals x to the 5th over 5 plus c. But we just found that c must equal 0. So that term actually cancels out. So we're left with the summation equaling x to the 5th over 5 plus these other terms. Simplifying further, where we have f of x equaling x to the 4th here, negative 1 over 1 factorial times negative a half, that's just positive 1/2 times x to the 4th. Looking at the next term, the 2 factorial in the denominator cancels out a 2 from that 4 factor, so I end up with 2 over 6 times x cubed. And then looking at that last term, I have 1 over 4 factorial times negative 1 over 30 times 24. The 4 factorial cancels the 24, and I'm left with minus 1 over 30 times x to the 1st equaling s of x. But we already know historically from Faulhaber's formula for sums of 4th powers that the sum from k equals 1 to n of k to the 4th equals 1/5 times open parenthesis n to the 5th plus 5 over 2 times n to the 4th plus 10 over 6 times n cubed plus 0n squared minus 5 over 30 times n. So now I need to show that these two formulae are equivalent. So to do that, I'm going to multiply the top equation by a creative form of 1 by 5 over 5. And when I do that, I distribute the 5 across to all of those terms. So that will give us 5 times x to the 5th over 5 plus 5 over 2 times x to the 4th plus 10 over 6 times x cubed minus 5 over 30 times x to the 1st. I'm going to cancel out terms here, and I'll get that this equation equals 1/5 times open parenthesis x to the 5th plus 5 over 2 times x to the 4th plus 10 over 6 times x cubed minus 5 over 30 times x to the 1st. Well, one is an equation in x and the other is an equation in n, but we see that they're the same exact equation. Very cool. The second application I want to look at is a very famous mathematical question called the Basel problem. And it was the solution of this problem that initially propelled Leonhard Euler to fame. So we'll introduce some new notation here. That's the Greek letter zeta. And we'll let zeta of x equal the sum from n equals 1 to infinity of 1 over n to the x. So this would equal 1 over 1 to the x plus 1 over 2 to the x plus 1 over 3 to the x, and so on. And so then zeta of 2 would equal 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on, which equals 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, and so on. Okay, so here's the Basel problem. We can see by the integral test that zeta of 2 converges, because if we take the integral from infinity to 1 of 1 over t squared dt, the convergence of this integral implies the convergence of the series. Well, this is an improper integral. It equals the limit as m approaches infinity of negative 1 over t evaluated at those endpoints at m and at 1. So that equals the limit as m approaches infinity of negative 1 over m minus negative 1 over 1. Well, that limit just goes to 0, and so we're left with this integral equaling 1. So because the related integral converges, we know that the series converges. But the important question here is, what does it actually converge to? And so the naive approach to the Basel problem would be to just start directly summing zeta of 2 and seeing whether it approaches some limit that we can easily recognize. The problem with that approach, however, is that direct summation of zeta of 2 is highly inefficient, because zeta of 2 actually converges very slowly. Now, to see why zeta of 2 converges so slowly, let's take another look at the integral of 1 over t squared dt, or I'll say here 1 over x squared dx. So to make it visual, I'll put down some coordinate axes here, and I'll start plotting some points on those axes and some points for the function y equals 1 over x squared. And now we'll connect them with that curve. So that's the curve of the function y equals 1 over x squared. And the sum of the Basel problem, zeta of 2, 1 plus 1/4 plus 1/9 plus 1/16 plus ... The value of that sum will be represented geometrically by the area enclosed by these rectangles, right? Because each of these rectangles has a base of 1 and a height of 1 over x squared. So this will be 1 plus 1/4 plus 1/9 plus 1/16. These are getting very tiny, so I'm just trying to represent visually that last rectangle will have an area of 1 over 25. Okay, so I'll add those terms to my sum for zeta of 2. And we can see that this sum is clearly bounded above by the curve for y equals 1 over x squared. So the area is bounded above by 1 plus the integral from infinity to 1, or 1 to infinity if you prefer, of 1 over x squared dx. So I'm just going to shade in that area here in purple to illustrate how zeta of 2 is bounded above by this area, 1 plus the integral from 1 to infinity of 1 over x squared dx. So why is that fact important? Well, if we want to manually sum zeta of 2, we want to manually sum 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 and so on, and we want to stop at some number. So we're going to truncate this sum somewhere. I mean, we have to if we're doing this manually. We want to truncate the sum at some number 1 over n squared. We know that the error in our sum will be close to and also bounded above by the integral from infinity to n of 1 over x squared dx. If we were to keep summing zeta of 2 manually past n, whatever that sum would equal would have to be less than the integral from infinity to n of 1 over x squared dx. And that integral actually equals 1 over n. Well, that's actually really bad news for us, because an error that's close to and bounded by 1 over n shows that we actually have very slow convergence for this sum. And to see that, just consider what would happen if we started manually summing just the first 10 terms of this series. Summing 10 terms in an infinite series really isn't a lot, but it's enough to show us what's going on here. So we want to sum 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36 and so on, plus 1 over 81 all the way up to 1 over 100. So how good of an approximation of zeta of 2 is that sum of the first 10 terms? Well, we know that our error bound, the maximum error, would have to be less than the integral from infinity to 10 of 1 over x squared dx. And when we evaluate that integral, that just equals 1 over 10, or 0.1. Well, that's actually a huge error. That's saying that we're not even confident to 1 decimal place after summing 10 terms of this series. If we summed the first 100 terms of this series, our error bound would be 1 over 100, or 0.01, and we wouldn't even be confident to 2 decimal places after summing 100 terms. We wouldn't be confident to 3 decimal places after summing 1,000 terms. 1,000 terms summed, and we're not even confident to 3 decimal places. I hope that gives you guys a sense of just how slowly this series converges. Well, I guess it's too bad that we can't get the result just by brute force computation, but that's in fact what motivated Euler to develop super powerful mathematics like the Euler MacLaurin Summation formula.
And he also discovered by other means what zeta of 2 actually equals. So for those of you that haven't seen this before, I hope you'll be amazed to learn
that zeta of 2, which equals 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on to infinity, that this infinite sum converges to pi squared over 6.
Well, the fact that that has anything to do with pi is truly amazing.
Some of you may also notice that it's pi squared multiplying 1 over 6, which is a Bernoulli number. We'll talk about that another time.
At any rate, we obviously can't prove this result by direct computation. We saw how slowly zeta of 2 converges. Euler proved this result through other means, which I'll talk about in another video for another time.
But part of the reason Euler was so confident that he had found that zeta of 2 equals pi squared over 6 is that he ran zeta of 2 through the Euler MacLaurin summation formula and got a result much closer to the true limit of zeta of 2 than could be found by direct computation. So again, it would take us too far off topic to show here how Euler discovered that zeta of 2 equals pi squared over 6. There are many other videos actually on YouTube that cover that material very well. But what I want to do in this video is show how we can apply the Euler MacLaurin summation formula to the Basel problem to get a very good estimate for zeta of 2, much better than we could get by direct summation. So here's how Euler did it. We'll let f of x equal 1 over x squared, right? Because that's the function whose values we're going to be summing on x equals 1, x equals 2, x equals 3, and so on, all the way up to infinity, in fact. So then by our formula, s of x equals f of 1 plus f of 2 plus f of 3 plus f of 4 and so on, all the way up to f of x. And this equals 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on, all the way up to 1 over x squared. And then by the Euler MacLaurin summation formula, s of x will equal the indefinite integral of 1 over x squared dx plus 1 over 1 factorial times 1/2 times f of x, or 1 over x squared here, plus 1 over 2 factorial times 1/6 times f prime of x, which equals negative 2 over x cubed, minus 1 over 3 factorial times 0 times f double prime of x, which equals negative 3 times negative 2 over x to the 4th, minus 1 over 4 factorial times 1 over 30 times f triple prime of x, which equals negative 4 times negative 3 times negative 2 over x to the 5th. And I'll put parentheses around these negative numbers just to make things very clear. So again, this is over x to the 5th. The next term is minus 1 over 5 factorial times 0, again, all the odd Bernoulli numbers greater than b sub 1 or 0, times f quadruple prime, which is 5 factorial over x to the 6th, okay, plus 1 over 6 factorial times 1 over 42 times negative 6 factorial over x to the 7th minus dot dot dot. So I'll just cross out those 0 terms there since they don't contribute anything, and I'll make some cancellations there. And now just to clean up the formula a little bit, making a few more cancellations across, this would equal, now doing the indefinite integral of 1 over x squared dx is negative 1 over x plus some constant c. And then our next term would equal plus 1 over 2 times x squared, and then it would be minus 1 over 6x cubed, and then plus 1 over 30 times x to the 5th, minus 1 over 42 times x to the 7th. And I'll just add one additional term there, plus 1 over 30 times x to the 9th. That would be the next non-zero term that we could very easily calculate. So we have this constant c that we need to determine,
And to figure out what c must equal, we can take the limit as x approaches infinity. Well, we know what the limit as x approaches infinity of s of x must equal. That would be summing up all of the terms, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, all the way up to infinity. That's just zeta of 2. And again, we know by other means that zeta of 2 equals pi squared over 6. So therefore, on the right-hand side of our Euler MacLaurin summation formula, all the terms that have x in the denominator go to 0, and we're left with c equaling pi squared over 6. So when we plug in pi squared over 6 for c into the Euler MacLaurin summation formula, we're able to then obtain a very good computational estimate of zeta of 2. And here's how we would do that. We're going to manually sum the first 10 terms of zeta of 2. So to do that, then we'll let x equal 10, and we can manually sum these terms up. So s of 10, we know what that would equal. We can just manually do it. S of 10 would equal 1 over 1 squared plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus 1 over 36 plus 1 over 49 plus 1 over 64 plus 1 over 81 plus 1 over 100. Now, I do like to show you guys all my steps, but you can just take a calculator and do this on your own. That equals 1.54976773111 ... We'll then plug x equals 10 into our summation formula. So I've done that here. I've substituted 10 for x into the formula. And we know that the formula should approximate this sum, 1.54976773111 ... Now let's work this process in reverse for a moment. Let's pretend that we don't know that c equals pi squared over 6. And we'll truncate our summation at that last term that I've written there, 1 over 30 times 10 to the 9th. So then this should be roughly equal to 1.54976773111 ... Let's rearrange this equation and solve for c. So when I do this rearrangement, I get s of 10 equals 1.54976773111 ... approximately equal to negative 1/10 plus c plus all these other numerical terms. And I find that c is therefore approximately equal to 1.54976777311. Okay, so now I'll move some terms over. Plus 1 over 10 minus 1 over 2 times 10 squared plus 1 over 6 times 10 cubed, 6 times 1,000, minus 1 over 30 times 10 to the 5th, or 10,000, plus 1 over 42 times 10 to the 7th, minus 1 over 30 times 10 to the 9th. And when we manually punch those digits into the calculator, we find that c is approximately equal to 1.644931066847490. Well, we know that c should equal pi squared over 6, so just how good of a numerical approximation is the Euler MacLaurin summation formula giving us? And the answer is incredibly good. Euler had other ways of knowing what pi equals and what pi squared equals, so he could compute that pi squared over 6 equals, to a high level of accuracy, 1.64493, and here's the first digit where our estimate is wrong, 4. But our estimate actually gets the next several digits correct after that before going completely off. So again, we saw that where manual summation of zeta of 2 couldn't even ensure accuracy up to 3 decimal places, after summing 1,000 terms, by just summing a handful of terms in the Euler MacLaurin summation formula, we're able to obtain an estimate for zeta of 2, which equals pi squared over 6, that's already accurate up to 5 decimal places, and looks like it's going to be accurate up to even more decimal places if we were only to add a few more terms. Euler actually approximated zeta of 2 to something like 17 decimal places using the Euler MacLaurin summation formula. However, even though the Euler MacLaurin summation formula is incredibly powerful, it would be a misconception to believe that adding more and more terms in this formula always gets you better and better approximations. In fact, because the Bernoulli numbers grow so rapidly, the Euler MacLaurin summation formula ultimately diverges.
In most cases.
The utility of the formula comes from adding enough terms to accurately approximate the sum you're looking for, and then truncating that sum before the Euler MacLaurin summation formula starts to diverge. So to be completely forthright, this derivation of the Euler MacLaurin summation formula is incomplete because it doesn't give us the error term for what's left over when we truncate the summation. As I already mentioned, the remainder term was discovered much later by Poisson, and I'll need to make a video later on in the series to fully explain it. But hopefully this served as a useful introduction to the Euler MacLaurin summation formula and some of its applications. So that's it for today. Thanks so much for watching, and if you enjoyed this video, please like or subscribe to my channel. Thanks.